Good afternoon, students. As usual, this is mathematics, part 3 of Newton-Raphson'S method, and we are going to look at derivations for nth roots. Let me just use the root of a number say n. So as usual, we are looking at the NRM. So, and we are going to use the examples this time around. You already know what we mean by NRM, the Newton-Raphson's formula. So we are going to say, first, the first question we are saying, derive the Newton-Raphson's method used to find the nth root. Let me use the kth root of a number say n. Now in the solution for this, when you want to derive the Newton-Raphson's method usually to find the kth root of a number say n, we need to first come up with the function, and the function here, we are going to start by saying let x be equivalent to a number n power 1 out of k for this case. This is what we call the kth root of the number n. It is given by n to power 1 over k. And from here, we are going to form an equation. What we do, we want to get rid of 1 over k, the reciprocity power. So we can start by powering k on both sides. So here we are going to have x power k, giving us n to power 1 out of k, but here power what? Power k. And as you look at this by laws of indices, if I have a number x power n to power m, this is the same as x power n times m. So basing on that, we can now say this x to power k is the same as n to power 1 over k times k, which cancels to 1. So this one is just xn equals to 1. Now from here, we are going to form the function this, and the left right hand side we are going to have a 0. So meaning we are going to transfer this n and have x to power k minus n is equal to 0. Then when we have this, we can now say let f of x be equals to x to power k minus n, and this is followed by the derivative of this function with respect to x. This will be k, drop the power, reduce the power by 1, and when I differentiate n, I get a 0. So this is the derivative of that. Then we can now substitute xn, and this is going to be xn power k minus n, and then the further derivative of xn is going to be k xn to power k minus 1. Then we quote the Newton-Raphson's formula, which says that xn plus 1 is the same as xn minus f of xn divided by the further derivative of xn. And this is the Newton-Raphson's formula. And then our xn plus 1 is going to be xn minus our function f of xn. We have it here, so we can bring and then put here as xn power k minus n divided by the further derivative is here, which is kxn to power k minus 1. Now it is upon us to simplify this function altogether. I believe this one happens to be a 1, and we can say xn plus 1 is equal to, now the LCM of the 1 and this function is simply this, which is kx n to power k minus 1. Get this function divided by 1 to get this function itself, which multiplies the numerator, which is this, into kxn power k minus 1. Then take away this function divided by this, we get a 1, which multiplies that. So we're going to have here xn power k minus this, and our xn plus 1 is now going to give us, when I expand this, I'll get something like k xn. Now here we have xn, here we have xn. So when I'm multiplying those two functions, xn times xn to power k minus 1, this xn has power 1. By laws of indices, if I have, say, xn times xn, if this one has power n and this one has power m, laws of indices, this is the same as x to power n plus m. We add the powers. So here we have 1, here we have k minus 1. So together we are going to add, and this one will give us xn to power simply a k. And this is what I'm going to get here. This one will get to power k. And to move on, this will be minus xn to power k, negative, and this negative will give us a positive n. And together here, we are dividing by kxn to power k minus 1. So this is xn plus 1 equals to, when I try to check out here, I get that this term is common. So I can easily factorize it out, and I'll remain here with k and here negative 1. So I'll have this, and here I have xn power k minus n, divide this by k of xn to power k minus 1. And this is for n equals to 0, 1, 2, 3, and so forth. So this is the Newton-Raphson'S formula for computing the kth root of a number, say, n. So from that we can derive the very many functions here, and I want to write them as proofs. And this comes to question number 2, which is going to be, show that the iterative formula based on Newton-Raphson'S method for finding the Roman 1. Roman 1, we're going to say square root of a number say n is given by xn plus 1 is equivalent to, going to have here xn power 2 plus n, and then we are dividing by 2xn like this, and this one we are going to say for n equals to 0, 1, 2, 3, and so forth. So this Roman 1, we're going to have to derive the n, the one for computing the square root of a number, say n, and we want to show that indeed it is given by this. Okay. So in our solution for number 1, for Roman 1, we are going to simply let the x to take on the x to power square root, means power half. And here we are going to simply try to remove the fraction of on the power, and this will give us x power 2 on both sides. It will be equals to n. When I power 2, this one will be able to create n. And here we are going to have x squared minus n equals to 0. This is the point where we're going to say let now f of x take on x squared minus n. Then the next step is to differentiate. The further derivative will now give us 2x only, because this is a 0. And obviously we can now put in the xn, is xn squared minus n, and then the further derivative of xn, which is the 2xn. Now from here we put the Newton-Raphson'S formula, which says that xn plus 1 is given by this over the first derivative of xn. And then it is upon us to now enter our functions we've obtained. So we are going to have xn plus 1 equals to the LCM. Here, before we take the LCM, I think we need to substitute. So we have xn minus our f of x is f of xn is xn squared minus n divided by 2xn. Now from here we simplify. LCM is 2xn. Here we have simple denominator 1. This one divided by 1 to get itself, times that we simply get 2xn squared, then minus this divided by that is 1, which multiplies that. I believe we simply get this. And this one now will give us 2xn squared. When I enter negative 1, here we get xn squared, and this negative 1 with negative n, we are going to create a positive n, divide it with the 2xn. And when you try to simplify this, you're going to have the solution as xn to power 2 plus n, and we are dividing this by 2 of xn. This is for n equals to 0, 1, 2, 3, and so forth, and that is the value for this to that. And we can as well say as required in this question, because the question required us to clearly bring up that solution. Now to candidates, when we have that, we can still give you a lot of functions. Say now Roman 3, I want us to derive for the nth root or for n power 1 over 3. So this one, let me say show that the NRM for finding Roman 1 n power a third. This is the cube root. So we are to show that the NRM for finding the cube root of a number, say n. So this is the Newton-Raphson'S formula. We want to show that this one is given by the cube root. It is going to be 2 out of 3 into xn plus n out of 2 xn power 2 for n equals to 0, 1, 2 onwards. Roman 3 n power, and here we can say the fourth root, and we want to show that it is given by xn plus 1 is given by 3 out of 4 into xn plus n over 3 xn power 3 for n equals to 0, 1, 2. Then Roman 4, I want to show the one for n, and this one we call it the fifth root. We want to show that is given by xn plus 1 is equal to 4 out of 5 into xn plus n out of 4 xn power 4 for n equals to 0, 1, 2,